Hi, this is our last video, our last QOD for chapter 15. And it is on Le Chatelier's principle, which has to do with how systems at equilibrium react to changes. And so ultimately, you really only need to understand this in a qualitative way. Although I'm going to use some sort of semi-quantitative methods for talking about why some of these things occur. Ultimately, you really only need to be able, when this is through, to predict the direction that an equilibrium would shift if a particular thing happened to it. So what does Le Chatelier's principle say? It says if you have a system at equilibrium and you disturb that, and the way you might disturb it is by changing the temperature or changing the pressure of a gaseous reaction or the concentration of a component, that is a reactant or product, the system will shift its equilibrium position so as to counteract the effect of the disturbance. You can think about a system at equilibrium as just sort of being like a person sitting outside, and if it starts to get cold, that person will, if the temperature goes down, that person will feel cold and they'll put a jacket on to counteract the effect of that. If it gets really hot and they'll start sweating, then they might take, the jacket off to counteract that effect, or they might take a drink of water because they've lost some water to perspiration, etc. So it's possible to think about a reaction simply as an individual with a mind of its own that is simply reacting to certain changes in its environment. So let's talk about what are the various ways in which a system at equilibrium could be disturbed. The first thing would be addition of a reactant or product. And so if I was a system at equilibrium and a reactant was added, then I would say, oh, I need to shift so as to consume some of that extra reactant. Or if a product was added instead, I would say, oh, I need to shift so as to consume some of that added product. I could also remove a reactant or product. If I removed a reactant, I would say, oh, I need to make more of that reactant, so I'm going to shift so as to make more of that reactant. If I remove a product, I would say, oh, I lost some product, I'm going to shift so as to make more of that product. There could be changes in pressure if it was a gaseous reaction. If I increase the pressure, then the reaction would say, oh, I need to shift in the direction that has fewer moles of gas to sort of decrease the pressure. If I decrease the pressure, I would say, oh, I need to shift in the direction that has more moles of gas to increase the pressure. And then if there were changes in temperature, if I were to heat it up, I would say, oh, if I'm the reaction, I would say, oh, I need to shift in the direction that consumes heat. If I were to cool it down, then if I were the reaction, I would say, oh, I need to shift in the direction that generates heat. So there's a two-slide summary of Le Chatelier's principle, and if you think you understand it well enough now from that description, that's fine. But I'm going to go on and talk a little bit more in detail as to why some of these things occur. And so to do that, let's consider the first thing, which would be adding a reactant to a reaction at equilibrium. So this is the synthesis of ammonia from nitrogen and hydrogen. And let's just say that I have this situation, I have this reaction at equilibrium. It has reached equilibrium. And I'm going to add some hydrogen to it. And so here, let me just explain this graph. Here it has reached equilibrium. It's just cruising along at equilibrium, no change. Then all of a sudden, at once, I spike in a bunch more hydrogen. Okay. What's going to happen? Well, what happens is that the reaction shifts toward products. And so you'll see that spike in hydrogen starts to get consumed. Because hydrogen is getting consumed, nitrogen must also get consumed, so its concentration goes down. Because the reactants are being consumed, the concentration of the products go up, which is the ammonia, and then eventually they reach a new equilibrium, and then they just continue at that equilibrium point. So if we're just thinking about this in terms of a reaction with a mind of its own, we would say the disturbance was that we added some hydrogen, and so the response was that it was counteracted by reacting away some of that hydrogen. So that's the sort of mind of its own explanation. We can also think about this, though, in a sort of semi-quantitative way. Because remember, when a reaction is at equilibrium, Q is equal to K. right? Now, what happens to Q if I add some hydrogen? Well, that means I'm increasing the concentration or the pressure of hydrogen, right? And hydrogen is a reactant. Reactants go in the denominator of the equilibrium constant expression. So if I add hydrogen, which is a reactant, that is going to have the effect of increasing the denominator and lowering the value of Q. So at this point, Q was equal to K, but I added a reactant. When that happened, now Q becomes less than K. And we learned earlier in the chapter that when Q is less than K, the reaction is going to shift toward products to reestablish equilibrium. So once more, I can think about it just in terms of, oh, I just had some product added, I just had some reactant added to me, I'm going to shift toward products to react it away. Or I just had some reactant added to me, that changes my Q is now less than K, therefore I must shift toward products in order to reestablish equilibrium. We can quickly summarize changes in concentration of reactants and products and what they're going to do in terms of shifting equilibrium in two senses. Let's talk about actions that will shift an equilibrium toward products. That would be either addition of a reactant, which is the one we just looked at with the addition of the hydrogen to that ammonia reaction, or removal of a product. Both of these things are going to decrease the value of Q, right? Adding a reactant increases the denominator, therefore Q goes down. Removal of a product decreases the numerator, therefore Q goes down. In either of these cases, Q is going to become less than K, and therefore the system is going to have to shift to the right to reestablish equilibrium. Let's consider actions that will shift the equilibrium toward reactants. That would be either removing a reactant or adding a product. And that's because removing a reactant increases the value of Q, right? Removing a reactant decreases the denominator and therefore increases the value of Q. Adding a product increases the numerator and therefore increases the value of Q. Both of those actions is going to cause Q to become greater than K, and therefore the equilibrium is going to have to shift to the left to reestablish equilibrium. Now, chemists use Le Chatelier's principle all the time, and as a former synthetic organic chemist, I can tell you that this is a major part of chemistry thinking when it comes to trying to get reactions to work that don't have particularly favorable equilibrium constants. And this is what's known as a Fischer esterification. When you mix isopentyl alcohol with acetic acid, you get a compound called isopentyl acetate, which is banana oil, and water. Now, these are all liquids. None of them is the solvent, so they all appear in the equilibrium constant expression, including the water, because it is not the solvent for the reaction. It's a product. Now, the K for this reaction is about 4, which means it does favor products, but only a little bit. If I started with a 1 molar solution of each of my reactants, I'm not going to show you all the math, but when you get to equilibrium, you've got about a 0.67 molar concentration of both of the products, but about 0.33 molar concentration of reactants remaining, which means that this only goes about 2/3 of the way and stops, which is okay, but you'd like to make this reaction go all the way to completion or as close as you can. So one way to do that, taking advantage of Le Chatelier's principle, is to add more of a reactant. So now I've redone this, in which I once more have a 1 molar solution of isopentyl alcohol, but now I'm using a big excess of the acetic acid, 10 molar, and therefore this now becomes my limiting reactant. If I went through all the math of this, which includes a quadratic equation, what I would find is now my limiting reactant is consumed not 2/3 of the way, but almost all of the way. There's only 0.03 molar left, and it goes 97%. So by this method of using an excess of one reactant, I can use Le Chatelier's principle to drive this reaction through toward products. Another way that I can use Le Chatelier's principle to drive this through toward products is, instead of concentrating on manipulating reactants, I can concentrating on manipulating products. Recall, one of the ways to drive a reaction forward is to remove a product as it's being formed. And one of the simplest things to remove as it's being formed is water. It is water, and chemists have a lot of different ways for doing this. This is what's known as a Dean-Stark trap, which is a mechanical method of what, if you're boiling your reaction, it will condense, and the Dean-Stark trap will actually collect the water in this little thing off to the side. So it's removing the water as it's being formed. Another way of removing water as it's being formed is a thing called molecular sieves. These are essentially little balls of brick dust that you heat up to a really high temperature in an oven until all the water has been removed from them. They love to absorb water into their little brick dust structure. If you just dump a bunch of these into your reaction, they will absorb water as it's being formed. And then this is phosphorus pentoxide, which likes to react with water to form polyphosphoric acid, which is also a solid. So if you just dump a little bit of this into the bottom of your reaction, that will suck water out as well. So whether it's by mechanical methods or physical methods or chemical methods, we can remove water from a reaction like this. And as long as we keep removing the water, the equilibrium is just going to keep driving forward. So these are methods that chemists use to use Le Chatelier's principle to get good yields in chemical reactions. So we've talked about changes in concentration. Let's talk about changes in pressure for a reaction at equilibrium. So again, we've thought about this. We've talked about gases in a syringe. We can change the volume and therefore change the pressure. Remember, the system is going to shift its equilibrium position so as to counteract the effect of the disturbance. And so there are a couple things. I could increase the pressure or I could decrease the pressure of a gaseous reaction. If I increase the pressure, the equilibrium, once again, if we think about this as someone with a mind of its own, the equilibrium is going to shift toward the side that has fewer moles of gas. It says, oh, the pressure just went up. I'm going to shift toward the side that has fewer gas moles to make the pressure go back down. If the pressure on the system is decreased, the equilibrium is going to shift toward the side that has more gas moles. I just lowered the pressure. The reaction says, oh my gosh, the pressure just went down. I'm going to shift toward the side that has more gas molecules to try and raise the pressure again. Well, once more, we can talk in a semi-quantitative way about why that actually happens. And let's just take a look at this simple reaction, the decomposition of dinitrogen tetroxide to make nitrogen dioxide. And the key thing here is that there's not the same number of moles of gas on either side. There's 1 mole of gas on the reactant side. There are 2 moles of gas on the product side. Now let's just assume we're at equilibrium. And so at equilibrium, Q is equal to K, and I've actually written the equilibrium constant expression in here. Now let's say I double the pressure. I've got this written in terms of concentrations, but if I double the pressure, that means I'm also doubling the concentration of each of these things. What happens when I double the concentrate? I was at equilibrium. Now I'm multiplying both of these concentrations by 2. But you'll notice I've got this one squared in the numerator because the coefficient there is 2. So I'm multiplying this by 2 and then 2 again. So I'm multiplying the numerator by 4 while I'm only multiplying the denominator by 2. That has the effect of ultimately multiplying the whole thing by 2. So when I double the pressure, Q is no longer equal to K. It's now equal to 2 times K. Well, remember, when Q is greater than K, the system is going to shift to the left. So if I increase the pressure, it's going to shift left, which once more is the side that has fewer moles. We can look at the reverse. And let's say, again, we're at equilibrium, which Q is equal to K. And now I am going to cut the pressure in half. That means I'm reducing the concentration of that by a factor of 2, or multiplying it by a factor of 0.5. I'm multiplying that by a factor of 0.5. Well, I'm multiplying the numerator by 0.5 twice, but I'm only multiplying the denominator by 0.5 once. That means that now, if I cut the pressure in half, Q is now equal to 1/2 of K. It's less than K. When Q is less than K, the system is going to shift to the right, which is the side that has, in this case, is the side that has more moles. So I've just kind of shown you in a semi-quantitative way If I increase the pressure, it's going to shift left, fewer moles. If I decrease the pressure, it's going to shift right toward more moles. What if I've got a reaction like this one in which there are equal numbers of moles on either side of the equilibrium arrow? And you'll notice again in the equilibrium constant expression, there are two concentration terms in the numerator, two concentration terms in the denominator. If I have the same number of gas moles on both sides of the equation, that means I've also got the same number of gas moles in the numerator as I have in the denominator, then changing the pressure does not have any change on the value of Q. Well, what about changes in temperature? Up to now, everything we've done, whether it's removing a reactant, adding a reactant, or removing or adding a product, or changing the pressure, was actually making changes to concentration terms in the equilibrium constant expression. There is nothing with regard to temperature that appears in the mass action expression, which is another name for the equilibrium constant expression. But it's nevertheless the case that changes in temperature will change the position of an equilibrium, and that's because changes in temperature actually change the value of the equilibrium constant. Now, I'm not going to go into detail into the math of this one because that takes too long, and as I said, at the end of the day, Le Chatelier's principle is really intended to be a qualitative thing. But here's the way to think about this then in a qualitative way. Let's think about an endothermic reaction. An endothermic reaction in which delta H is greater than 0 is a reaction that absorbs heat while it occurs. And therefore, we could write the reaction this way, that reactants plus heat give products, because an endothermic reaction absorbs heat. Therefore, we can treat heat in this case as a reactant. And in that way, we can go back to thinking about this in terms of Le Chatelier's principle. Increasing the temperature, that is adding heat, has the effect of adding a reactant, and therefore it will shift the equilibrium toward products. Decreasing the temperature has the effect of removing heat, which we consider in this case to be a reactant, and removing a reactant will shift the equilibrium back toward reactants. So for an endothermic process, raising the temperature moves it toward products, lowering the temperature moves it towards reactants. What about an exothermic reaction? Well, an exothermic reaction generates heat, produces heat, and so we can write it this way: reactants react to give us products plus heat, and therefore we can treat heat as a product, and therefore we can once more apply Le Chatelier's principle. If I increase the temperature, that has the effect of adding heat, which is adding a product, which will shift the equilibrium toward reactants. If I lower the temperature, that has the effect of removing heat. I am removing a product, therefore the equilibrium is going to shift toward products. Well, that's everything you need to know about Le Chatelier's principle in terms of being able to do this for an assessment. Let me just give an example, and this is actually this has to do with changes in temperature. This is part of the experiment that we're doing this week in the lab on equilibrium. This is the equilibrium between what's called the cobalt it's hexaquo cobalt complex and the tetrachlorocobalt complex. What's interesting about these things is that this particular complex ion has a pink color. This particular complex ion has a blue color. And so if you just have cobalt in water without a lot of chloride around, it'll be pink. If you have cobalt with a lot of chloride around, you'll get this blue color. Okay, well, this is an endothermic reaction. That is, the delta H is greater than 0. So let's think about this. If an endothermic reaction is heated, it will go toward products. If an endothermic reaction is cooled, it will go toward reactants. And so if you were able to get this so you had sort of a purple mixture of the two, which is kind of the goal of the lab experiment. So you start with a purple mixture in which you're like right on a 50-50 knife's edge of equilibrium here. If you heat that, you are adding a reactant to an endothermic reaction. Therefore, it's going to shift toward the blue. If you cool it, you're removing heat, removing a reactant from an endothermic reaction. It's going to shift toward pink. One last thing we want to say something about is catalysts. And let's just remind ourselves so the question is, what does a catalyst do to a system at equilibrium? Well, let's remember actually what a catalyst does when it comes to a reaction energy diagram. A catalyst lowers the energy of the transition state. Therefore, a catalyst lowers the activation energy barrier. A catalyst does not do anything to change the relationship between the potential energy of the reactants and the potential energy of the product. Rate is dependent on the activation energy. Equilibrium, the equilibrium constant, is dependent on the change in delta G, difference in delta G between reactant and product. A catalyst will change the value of activation energy. A catalyst will not change the value of delta G. And therefore, when you use a catalyst, it will reach equilibrium faster, but once you've reached equilibrium, then it's not going to change anything. So in other words, if you add a catalyst to a system at equilibrium, no detectable change will occur. If you add a catalyst to a system that has not reached equilibrium, it will reach equilibrium faster from either direction, because it lowers the activation energy for both forward and reverse reaction. Well, finally, what's the sort of question you'd be likely to see, this being a qualitative sort of topic? Well, here is a classic Le Chatelier's principles question. I've got a reaction here, 2SO2 plus O2 gives me 2SO3. This is a gaseous equilibrium in which 2 moles of sulfur dioxide plus 1 mole of oxygen give me 2 moles of sulfur trioxide. And it tells me that it's exothermic, which is an important thing to note. And it asks, which of the following is going to result in an increase of the number of moles of SO3 in the reaction container? So what's that really asking me? It's asking me which of these 5 things is going to cause this equilibrium to shift toward the right, to shift toward products, because it's asking which is going to increase the amount of SO3. So let's take the first one first. What's going to happen if I decrease the pressure? Well, remember, if I decrease the pressure, it's going to shift toward the side that has more gas moles, which is the reactant side. And so that can't be my answer. What about increasing the temperature? Well, it says that this reaction is exothermic and therefore heat is a product. If I increase the temperature, I'm adding a product, which is going to shift it back toward reactants. That's not my answer. If I remove some oxygen, I'm removing a reactant. Remember, the effect of decreasing a concentration of a reactant is to shift the equilibrium back toward reactants. So that's not my answer. What about increasing the pressure? Increasing the pressure on a gaseous reaction is going to shift it toward the side that has fewer moles. The right side here has fewer moles than the left, so D is looking pretty good. Let's just check E, increasing the volume of the container. Well, increasing the volume of a container in a gaseous reaction is the same as decreasing the pressure. We've already decided that decreasing the pressure is not the correct answer. And therefore, the correct answer is D. If I increase the pressure, it's going to shift toward the side that has fewer gas moles. That's the right-hand side. I'm going to increase the number of moles of SO3. Okay, please take a moment after watching this to look through some of the suggested practice problems, and look forward to seeing you for the QOD in class. Thanks for watching.